I'd like you to think about how I'm doing this right now. Not why I'm doing it, because of course I'm doing it because I like music and I like science and I like to do both those things at the same time. But how can I play music? How can I be hearing it right now? How can I walk around and play my guitar at the same time without falling on my face? And what is even sound anyway?
These are all good questions. Let's start with the last one first. The basic answer to what is sound goes like this. Sounds create vibrations in the air that beat against the eardrum, which pushes a series of tiny bones that move internal fluid against a membrane that triggers tiny hair cells, which aren't actually hairs, that stimulate neurons, which in turn send action potentials to the brain, which interprets them as sound. But there's a lot more to our ears than allowing us to experience the pleasure of birdsong or the pain of grindcore. The ear is often overlooked, but even more vital role is maintaining your equilibrium, and without that, you wouldn't be able to dance or strut, even stand up, and you definitely could not do this. At least not without throwing up. In order to really get to the nitty-gritty of how your ears pick up sound, you gotta understand how sound works. The key to sound transmission is vibration. When I talk, my vocal folds vibrate. When I slap this tabletop or strum a guitar, those vibrations cause air particles to vibrate too, initiating sound waves that carry the vibration through the air. So this sounds different than this, because different vibrating objects produce differently shaped sound waves. A sound's frequency is the number of waves that pass a certain point at a given time. A high-pitched noise is the result of shorter waves moving in and out more quickly, while fewer, slower fluctuations result in a lower pitch. How loud a sound registers depends on the wave's amplitude, or the difference between the high and low pressures created in the air by that sound wave. Now, in order for you to pick up and identify sounds from beeping to barking to Beyonce, sound waves have to reach the part of the ear where those frequencies and air pressure fluctuations can register and be converted into signals that the brain can understand. So once again, it all boils down to action potentials. But how does sound get in there? Your ear is divided into three major areas: the external, middle, and inner ear. The external and middle ear are only involved with hearing, while the complex hidden inner ear is key to both hearing and maintaining your equilibrium. So the pinna, or auricle, is the part that you can see and wiggle and grab or festoon with an earring. It's made up of elastic cartilage covered in skin, and its main function is to catch sound waves and pass them along deeper into the ear. Once a sound is caught, it's funneled down into the external acoustic meatus, or auditory canal, and toward your middle and inner ear. Sound waves traveling down the auditory canal eventually collide with the tympanic membrane, which you probably know as the eardrum. This ultra-sensitive, translucent, and slightly cone-shaped membrane of connective tissue is the boundary between the external and the middle ear. When the sweet sound waves of your favorite jam collide with the eardrum, they push it back and forth, making it vibrate, so it can pass those vibrations along to the tiny bones in the middle ear. Now, the middle ear, also called the tympanic cavity, is the relay station between the outer and inner ear. Its main job is to amplify those sound waves so that they're stronger when they enter the inner ear. And it's got to amplify them because the inner ear moves sound through a special fluid, not through air. And if you've ever gone swimming, you know that moving through a liquid can be a lot harder than moving through air. The tympanic cavity focuses the pressure of sound waves so that they're strong enough to move the fluid in the inner ear. And it does this using the auditory ossicles, a trio of the smallest and most awesomely named bones in the human body, the malleus, incus, and stapes, commonly known as the hammer, anvil, and stirrup. One end of the malleus connects to the inner eardrum and moves back and forth when the drum vibrates. The other end is attached to the incus, which is also connected to the stapes. Together they form a kind of chain that conducts eardrum vibrations over to another membrane, the superior oval window, where they set that fluid in the inner ear into motion. The inner ear is where things get a little complicated, but interesting and also kind of mysterious. With some of the most complicated anatomy in your entire body, it's no wonder it's known as the labyrinth. This tiny, complex maze of structures is safely buried deep inside your head because it's got two really important jobs to do. One, turn those physical vibrations into electrical impulses the brain can identify as sounds. And two, help maintain your equilibrium so you are continually aware of which way is up and down, which seems like a simple thing, but it's very important. To do this, the labyrinth actually needs two layers. The bony labyrinth, which is the big fluid-filled system of wavy wormholes, and the membranous labyrinth, a continuous series of sacs and ducts inside the bony labyrinth that basically follows its shape. Now, the hearing function of the labyrinth is housed in the easy-to-spot structure that's shaped like a snail's shell, the cochlea. If you could unspool this little snail shell and cut it in a cross-section, you'd see that the cochlea consists of three main chambers that run all the way through it, separated by sensitive membranes. The most important one, at least for our purposes, is the basilar membrane, a stiff band of tissue that runs alongside that middle fluid-filled chamber. It's capable of reading every single sound within the range of human hearing and communicating it immediately to the nervous system, because right smack on top of it is another long fixture that's riddled with special sensory cells and nerve cells called the organ of Corti. So when your cute little ossicle bones start sending pressure waves up the inner fluid, they cause certain sections of basilar membrane to vibrate back and forth. This membrane is covered in more than 20,000 fibers, and they get longer the farther down the membrane you go. Kind of like a harp with many, many strings, the fibers near the base of the cochlea are short and stiff, while those at the end are longer and looser. And just like harp strings, the fibers resonate at different frequencies. More specifically, different parts of the membrane vibrate depending on the pitch of the sound coming through. So the part of the membrane with the short fibers vibrates in response to high frequency pressure, and the areas with the longer fibers resonate with lower frequency waves. This means that all of the sounds you hear and how you recognize them comes down to precisely what little section of this membrane is vibrating at any given time. If it's vibrating near the base, then you're hearing a high frequency sound. If it's shaken at the end, it's a low noise. But of course, nothing's getting heard until something tells the brain what's going on, and the transduction of sound begins when part of the membrane moves and the fibers there tickle the neighboring organ of Corti. This organ is riddled with so-called hair cells, each of which has a tiny hair-like structure sticking out of it, and when one is triggered, it opens up mechanically gated sodium channels. That influx of sodium then generates graded potentials, which might lead to action potentials, and now your nervous system knows what's going on. Those electrical impulses travel from the organ of Corti along the cochlear nerve and up the auditory pathway to the cerebral cortex. But the information that the brain gets is more than just like, hey, listen up. The brain can detect the pitch of a sound based solely on the location of the hair cells that are being triggered. And louder sounds move the hair cells more, which generates bigger graded potentials, which in turn generate more frequent action potentials. So the cerebral cortex interprets all those signals and also plugs them into stored memories and experiences, so it can finally say, oh, that's a chickadee, or a knock at the door, or the slow burn of an 80s saxophone solo, or whatever. So that's how you hear. But we're not done with you yet. We gotta talk about equilibrium. The way we maintain our balance works in a similar way to the way we hear, but instead of using the cochlea, it uses another squiggly structure in the labyrinth that looks like it's straight out of an alien movie, a series of sacs and canals called the vestibular apparatus. This setup also uses a combination of fluid and sensory hair cells, but this time the fluid is controlled not by sound waves, but by the movement of your head. The most ingenious parts of this structure are three semicircular canals, which all sit in the sagittal, frontal, and transverse planes. Based on the movement of fluid inside of them, each canal can detect a different type of head rotation, like side to side, and up and down, and tilting, respectively. And every one of the canals widens at its base into sac-like structures called the utricle and saccule, which are full of hair cells that sense the motion of the fluid. So by reading the fluid's movement in each of the canals, these cells can give the brain information about the acceleration of the head. So if I move my head like this, because I'm like super in my jam, that fluid moves and stimulates hair cells that read up and down head movement, which then send action potentials along the acoustic nerve to my brain, where it processes the fact that I'm bobbing my head. And just as your brain interprets the pitch and volume of the sound by both where particular hair cells are firing in the cochlea and how frequent those action potentials are coming in, so too does it use the location of hair cells in the vestibular apparatus to detect which direction my head is moving through space, and the frequency of those action potentials to detect how quickly my head is accelerating. But things can get messy. Doing stuff like spinning on a chair or sitting in a rocky boat can make you sick because it creates a sensory conflict. In the case of me spinning around in my chair, the hair cells in my vestibular apparatus are firing because of all that inner ear fluid sloshing around, but the sensory receptors in my spine and joints tell my brain that I'm sitting still. On a rocking boat, my vestibular senses say I'm moving up and down, but if I'm looking at the deck, my eyes are telling my brain that I'm sitting still. The disconnect between those two types of movement, by the way, is why we get motion sickness. It doesn't take long for my brain to get confused and then mad enough at me to make me barf. I'm sorry that we're ending with barf, but we are. Today, your ears heard me tell you how your cochlea, basilar membrane, and hair cells register and transduct sound into action potential.
Let's talk about a couple of things.